Okay, on this video we're going to see if we can identify the unknown molecule that is represented in these graphs of the three spectroscopic techniques of mass spectroscopy, carbon-13 NMR, and the infrared spectra. So you can see that we've got the three distinctive graphs there: mass spec measured in MZ, carbon-13 NMR with parts per million measured, and the IR that's measured in inverse of wavelength centimeters, -1. Okay, so if we look at the mass spec graph for a start, we can see that the peak that is furthest to the right, we can just see it on the right here, is at 88 MZ, right? Now what that means here, because this is at 88 MZ, remember that is the molecule has gone through the mass spectrometer and it's been charged, and it's gained a positive charge, so it's the full molecule with the positive charge. It's the one most to the right, and in fact if we could look very closely at it, we'd see that there's a little tiny M+1 peak just to the right of that peak, but we ignore that because that just arises because of extra mass caused by carbon-13 isotopes. Anyways, so because this is 88 MZ, then we're going to state here, because what we're looking to do is, if we're writing the report for achievement standard 91388, that is the spectroscopy achievement standard 3.7 for NCEA for a level 3 chemistry, what we need to do is we need to identify two aspects from each graph for achieved, but if we want to attain a merit or higher, we need to explain how we identified the aspect of the molecule using the graph. So here I've said, okay, 58 MZ, that means that the molecule has a mass of 58 grams per mole. The second aspect we can identify from the graph, there's actually two of them. So we've got this peak here at 43, and we've got this peak here at 29. Now you might recognize that fragments this size 29 and 43, commonly can be attributed to coming from the following fragments: this C2H5 fragment, this charged fragment that's broken off the molecule, and this C3H7 fragment. Okay, so the first one here is the fragment. If we add up the molar mass of all the atoms in here, then the combined molar mass is 29. And with the second fragment, the combined molar mass is 43. So we have both of these present. Now, the second one is just, the one on the left is just a part on the one on the right. But what we can see is we must have 3 carbons joined to each other. Now, and that's what we need to have in our molecule. Okay, let's go on to the next graph. So this is a carbon-13 NMR graph. What we can note here is that there are 4 distinct peaks. Because there are 4 distinct peaks on this graph, they must have originated from carbons that are in unique environments. So there must be 4 unique carbon environments, okay, and 4 different unique places on the molecule that the carbon atom can be. So that's the first thing we can state. Okay, so that's a nice aspect, easy aspect to state for this graph. Hey, just going back to the previous graph, mass spec, if you want to make sure you have a full amount of aspects to talk about, one thing to notice is there is no M+ to M+2 peak either. So you could state, because there are no M+ to M+2 peaks, that is, the M+ has another peak 2 away from it, the M+ peak is another 2 away from it, in the ratio of 1 to 1 or 3 to 1, there is no bromine or chlorine. So that's another aspect you could state, and I always, if I'm writing a report, just put that down anyway. Just like I could also say, hey, the molar mass was even. That means that there's not going to be a single nitrogen in this molecule, because if you have a nitrogen in a molecule, always in one or an odd number of nitrogens, you always end up with an odd molar mass. Okay, let's get back to this carbon-13 NMR graph. Okay, so we can see these two ones here. So one at 21 and one at 13. The one at 13 is definitely just going to be bonded to the carbon that it represents is only going to be bonded to other carbons or other hydrogens, and the 21 is likely to be. Anything less than 20, it definitely is not bonded to a more electronegative element like a nitrogen, a chlorine, or an oxygen. But see this one here at 171 parts per million, it's in the range here, the range between 160 to 220 of where we would have a carbon that is double bonded to an oxygen or carbonyl group. So we can go ahead and state that the peak at 171 indicates a carbon environment with a carbon double bond carbon present. Cool. So we know that that's going to be present in the molecule because we can see it here. And now this green one here, what we can do is we can see it's at 61. Now 61, if we're somewhere between, I guess, 50 and 70 or somewhere around there, it's being shifted by an electronegative atom, and we're commonly just looking at oxygens, chlorines, and nitrogens. Oxygen shifts it the most, and this is in the range where we would find carbons that bonded to a single bonded to an oxygen would be shifted. So we're going to go ahead and say that we believe that this is most probably, so I've used the word could, right? So not definitive statement, but most likely it's going to be a carbon single bond carbon. Now, this is really important to note. That means that there is a carbon here that is bonded to an oxygen, a double bond oxygen. Then there is another separate carbon that's bonded with a single bond to an oxygen. So there must be at least 2 oxygens present. And the other thing we can note here is there's 1, 2, 3, 4 carbons. So there must be at least 4 carbon atoms. So at least 4 carbon atoms and 2 oxygens. Anyway, let's have a look at the IR here. So we're only looking to the left of the 1500. Anything to the right is called the fingerprint region. This is not a good place to look for evidence of stretches or bends of specific bonds. And the reason for that is they're not always strong and in the same place. However, it can be used to identify a molecule if I know what its graph should be beforehand. Hence, it's anything to the right of 1500 here is called the fingerprint region. Now, what we can notice here is that there is a strong peak at 1740 here, okay, centimeters -1. And we know that that's in the range that originates from a carbon double bond oxygen stretch. So that indicates that there is a carbon double bond oxygen functional group. Okay, so there is a stretch of that bond, and because of that we know that that group is present. Now that statement can be kind of tricky to explain that, but you actually have to recognize that the peak represents the stretch. That is, like, you think about it like the carbon and oxygen is a spring and they're pulling apart, and then they're going back together, and they've got this resonance or this sort of rhythmic movement away and back again. That stretch, okay, causes that peak. Now, because that stretch is present, it means there must be a carbon double oxygen group in this molecule. Okay, the other peak we see here, we're just going to label this, but this is going to be present in most molecules you look at, and that's the carbon-hydrogen stretch at around 3000. We usually don't use this to identify specific structures in a molecule because just about all the molecules we look at do have carbon hydrogens. But if it isn't there, if there's an absence of it, we can say that there's not a carbon and a hydrogen bond. Right, talking about absences, what we can see is there is not another little peak here about 1600. So there is not, it doesn't appear that there's a carbon double bond carbon. Now sometimes that carbon double bond carbon peak can be enveloped by this carbon double bond oxygen peak, but usually you see it as a wee peak just to the side of it. We can't see it, so we don't think there's a carbon double bond. But if we go back and look at the carbon NMR one, we definitely don't see anything in between the range of 100 and 140. So there's no evidence there of any carbon environments with a double bond. So I'm just going to say here, from this graph, I have no evidence of a carbon double bond stretch. And you know what else I don't see? I don't see this broad peak here that comes from an OH stretch. So there's no evidence of a carbon double bond carbon or an OH stretch. It's really important when you're writing these reports to include all information that's available, and that includes negative information, right? So this is negative information, what's not there. Remember when I went back to the maths one, I could also talk about what wasn't there. There's not the M plus, the M plus 2, peaks in the 1-to-1 or the 3-to-1 ratios we'd expect from bromine and chlorine, so you could say that they're not in a molecule. Okay, so that's very helpful information. We're trying to rule out what is not in the molecule. Okay, so if we go back and now we're going to look at integrating or putting two bits of information together that support each other to say something is there. Both on the NMR group graph here, right, at 171, we can see that there is evidence that there is a peak, a carbon-oxygen functional group, and we can see that also from the 1740 peak in the IR. So if we bring those together, we can say we're pretty confident that that carbon double bond oxygen is there because it's been indicated in two places. The other thing we can say is because there is an absence of this carbon double bond carbon peaks on the carbon NMR, and also one that we can't notice on the IR, we're pretty sure there's not a carbon double bond carbon in there. Okay. We can also here, remember I talked about this before, we said that there were 4 unique carbons, there must be at least 4 carbons, but we also know that there are 2 oxygens present because this green peak here and the blue one are both represent that they're attached to an oxygen, a double bond and a single bond here. So because we know that there's 4 carbons and 2 oxygens, 4 carbons equals 48, 2 oxygens are 32, that's a molar mass of 80, and if I add those 6 atoms together, molar mass of 80, since the actual measured molar mass is 88, there are 8 other hydrogen atoms that would be on this molecule to give a combined total of 88 grams per mole as our molar mass. Now if I take that together, I will draw this molecule. Now notice here in this molecule, what I've drawn is I've drawn 4 unique carbon environments. Each carbon environment is in a different place. I've also drawn my carbon bonded to an oxygen. Here it is, but it can't be bonded to an oxygen that is part of an OH because there's no evidence of an OH on the infrared graph. I've drawn this line of carbon atoms, or this fragment that would produce the 43 peak. Here it is here. And I've drawn the carbon double bond oxygen that is represented. Now, let's just check this over. This blue carbon here is corresponds to the carbon NMR of the 171 peak, right? Because this is a carbon double bond. This green one here is going to represent this carbon that's bonded to the oxygen. And as we get further away from the oxygen, because this carbon is just bonded to a carbon that's bonded to the oxygen, that's most probably why it makes it a bit higher at 21. So this one's going to be 21. And the one that's furthest away from the electronegative atom is going to be the 13. So this is quite strong evidence that this is our molecule. This cannot be, if we had to explain why it can't be why it can't have the second carbon coming off here, that would be because we would have 2 identical carbon environments, which would give us 3 overall. Okay, so I guess the last thing we can do is just summarize all of this up. So the molecule has a carbon bonded to oxygen. We talked about that. That's the green one, as well as a carbon double bond oxygen functional group. The blue one there has 4 unique carbon environments. Okay, and the CH that was attached. Oh, sorry. Yeah, this is another interesting point. If one of the CHs had been attached to here, 2 things. First, we wouldn't get this large fragment. But also, if there was another carbon on the right attached to the carbonyl group here, what we would get is we would see it shifted considerably more. It would be about 40. Okay. Now, we don't see any that are at 40, so it's quite strong evidence that there's no carbon bonded to the carbon that has the bond oxygen, because that carbon environment gets shifted quite considerably up to about 40. So that's quite strong evidence. And we can be quite confident then that this propyl methanoate is the molecule, the unknown molecule here. Hopefully this has helped you go through how you might write a report, how you might identify the aspects that are needed to construct the molecule that we think might be the answer, and look out for the other examples that I've done.